All right, this is the section where things start to actually get a little bit interesting. We're going to talk about the dot product, which is another operation on vectors, and projections, which is something you can compute using the dot product. So, as usual, the main questions we want to talk about: how do we define the dot product? What's its relationship to the other operations we defined in the previous section? And then how do you use it? What's the point? So the definition seems a little strange at first. The dot product takes two objects of one type and yields an object of a different kind. Okay, and that's probably a first if you haven't encountered vectors before this class. So it takes two vectors and what it gives us is a scalar. In other words, if I have the two vectors v and w, I define the dot product like this. So I multiply the corresponding components and then I add those products up. So if these are my vectors v and w, that's the dot product. Okay, pause, maybe take a moment, make sure that that makes sense, and then on the next slide, try a couple of them. So hit pause, take these two dot products, make sure you get the right answers afterwards. For this first one, I get 1 times 2, 4 times 2, 5 times 1. I add those products up, and I should get 15. Now for the second one, you have to be a little bit careful. Remember the IJK notation is a little bit different. That first vector doesn't have a j, which means the j component is 0. So I have 3 times 1, 0 times minus 10, minus 2 times 1. So at the end, 3 minus 2 gives us 1. The dot product of the two vectors is 1. So here's the question. Why do we care? Like, that's an operation that takes complicated things and turns it into something really simple, just a number. So, okay, for one thing, let's talk about why we call it a product. It's called a product because it distributes across addition, just like multiplication with numbers. It's commutative, meaning just like multiplication, the order can be done either way. V dot W is W dot V. And another kind of strange property that pops up is that you can talk about the norm as just the dot product of a vector with itself. Okay? For practice's sake, if you're uncomfortable with any of this stuff so far, or if you don't have a lot of vector practice from the past, make up a vector v, a vector w, a vector a, and confirm that all these things are true. So, to the question of what it does for us, do you remember the law of cosines? I will take that silence as a resounding yes. It's just the generalized Pythagorean theorem. In other words, if I have a non-right triangle, that's what the law of cosines tells me. Notice, if theta is 90, then cosine of theta is 0, so you just have the Pythagorean theorem. So this tells you, what do you do if it's not a 90-degree angle? Okay? Let's take that same diagram and let's redraw it in terms of vectors. So I could take the bottom side and make it a vector v. I could take the left side and make it a vector w. Now I could define a new vector for the long side, but if you remember from the previous section, I can close the triangle by taking the difference of v and w. Okay? Again, if that seems funny, hit pause, go back to the previous notes or slides or video, and revisit that to make sure that the difference operation makes sense. So I could take the law of cosines as it's written with a's, b's, and c's and rewrite it with vectors. Okay? And in particular, to be more specific, with lengths of vectors, because vectors have direction and magnitude, and I just want lengths here. Okay, so take a moment, make sure that that all seems okay. Okay, given the law of cosines, we'll just take it for granted. I could draw the diagram with vectors and then write the law of cosines with vectors. Now, forget like being scared by the derivation that's about to take place or remembering any of this stuff. You just have to remember the final result here. But I'm going to ask that you follow along here because there are a lot of properties that come up with each step that are important for you to understand. So for example, I can expand the first term by writing it as a dot product of v minus w with itself. And then we just said that that distributes. The dot product distributes across sums and differences. So actually you get that. And then again, v dot v is the norm of v squared. So we end up with that. Okay? So I don't care if you memorize all this, but hit pause and make sure that those 3 lines make sense to you. Then I'm going to take that and plug it back in. Okay, so all I've done is replace the left-hand side with the expanded version. Notice that norm v squared is on both sides, so that cancels. Norm w squared is on both sides, so that cancels. We're just left with that. And those minus 2's don't need to be there because I can divide. So we're just left with that. Putting all the vector stuff on one side, we get that cosine of theta is the dot product of v and w divided by their lengths, by their norms. So that's the power of the dot product. It tells you the angle between two vectors. You just have to be careful to scale the vectors so that they're of length 1. Okay? Because notice the right-hand side, it's the unit version of vector v times the unit version of vector w. Okay, couple of things. So first of all, I can conclude just by looking at the dot product whether the angle is acute, obtuse, or 90 degrees. And I can tell that by whether the dot product is positive, negative, or 0. So remember this property. This is something that we're responsible for remembering. If v dot w is positive, then cosine is positive. And cosine is positive in the first quadrant, so the angle's acute. If v dot w is negative, cosine is negative. That's in the third quadrant, so the angle's obtuse. If v dot w is 0, we've got a 90-degree angle. Okay, and knowing when things are perpendicular is going to be important. Now, again, this is one of those instances where there's a slightly different word that we can use that we don't have to use, orthogonal. Orthogonal is vectors, refers to vectors that are 90 degrees apart. All right, application stuff. Say I have two vectors v and b, and we draw v and b tail to tail. That's easy to do. I'm allowed to move vectors around wherever I want. I'm going to make b longer than v. Just for the sake of this illustration, it just makes it easier to draw. It doesn't have to be. So there we go. Now, drop a line perpendicular from the tip of v to b. Like that. What I want to do is find these two vectors that I've drawn lightly over the picture. Okay? I want to draw the vector in the direction of b, but that ends where that perpendicular stops. That vector is called the projection of v onto b. And you can think of it as like what happens if I shine a light down on the picture. If I shine a light down on the picture, the shadow that v casts is the projection. Now let's look at how we compute it. So it's written like this, sometimes with the arrow over projection, sometimes not, it doesn't matter. The subscript is the one you project onto. Okay, so that's v projected onto b. It should be clear from the picture, hopefully, that the length of the projection is the length of v times cosine of theta. Take a moment to make sure that that makes sense for you. So v is now the hypotenuse of this picture. The projection is the adjacent side. So the projection's length should be hypotenuse times cosine of theta. Now, what else do we know? We know that b divided by norm b has a length of 1. I don't know what the length of the projection is exactly, right? But I do know that if I take the unit vector b over norm b multiplied by the projection's length, that is the projection vector. Right? It's a little redundant. It's saying that if you take a unit vector times the length of the projection, you get the projection. So let's put it all together. I have the first fact, which is the straight up trig information. I have the second fact, which is the sort of redundant fact. Now, let's take norm v cosine and put it in place of the projection length. Then we get this expression. Well, I know that cosine of theta is v dot b over the norm v times the norm of b. Right? We learned that a few slides ago. The norm v's cancel, and I get the projection. Now, as an application, let me reiterate, you don't have to remember that derivation. I would never expect that you come up with that on your own. It took us 10,000 years to invent calculus. You can't be expected to do it in 12. But it's important to make sure that all those steps we just went through make sense and to be able to apply the result. Okay, so here's an application of the result. Say I want to find the distance from a point A to a line that goes between 2 points P1 and P2. Okay, so I'm keeping the projection picture there just so we can think about how it applies here. But here's the point A. Here's the line from P1 to P2. So the question is, how does the projection thing apply? And more importantly, like, how am I going to use vectors in here? Because we're all about vectors now. Well, I could, for one thing, just start connecting stuff. Okay? I'm going to make P1 to A my V vector, sorry. And I'm going to make P1 to P2 my B vector. And then I can drop a perpendicular, and all of a sudden, it looks like the projection diagram just tilted to the side a little bit. So that perpendicular to B is the length that we want. That's the distance. And the projection is the shadow cast on the vector B. So now let's do some actual computing. Here's our picture again. The vector V is the vector that connects P1 to A. And go back to the vector notes if this seems unfamiliar. You find that vector's components by taking the difference of the x's, y's, and z's. And then the same goes for the vector B. B connects P1 to P2, so I take the difference of the P2 components minus the P1 components. Now, the projection takes a little bit of work. It's the dot product of those divided by the norm of B squared times B. So we take the dot product, we divide by the norm squared. Notice I just got rid of the square root sign. You get 15 over 45 for that scalar. So that gives us the vector minus 2, 0, 1. So that shadow that's cast onto B, that projection vector, is the vector minus 2, 0, 1. Now, the difference of two vectors closes the triangle. So V minus the projection connects the projection's end up to the point A. And that vector has a length, which is the distance from the point to the line. So take the length of that vector, that's the distance. All right, this lecture covers a decent amount of important stuff, so go back to the beginning, just make sure you can compute dot products. That's really pretty straightforward. Make sure you memorize the formula for the projection, and I really would encourage you to go through how we derived it to help with the memorizing part. And then do some of the examples in the dot product section.